Okay, so I think it came up a few times, definitely to talk about the different extremes of fluid flow and Reynolds number dependence, limits of, in extreme limits of Reynolds numbers, we get interesting things that happen. And in one of them that is really nice is the creep flow region, and I don't think we did really anything with it beyond just talking about it. But here we just have a sphere falling through really, really highly viscous fluid. And what's nice here is I don't have to deal with any numbers, and there's no angles. Yes. Okay, so let's just say we can then, if we know the density of a sphere, we can go to the lab and measure its terminal velocity. We know the density of the liquid it's falling through, and and we don't know the viscosity of that liquid, but we know that it's a highly viscous fluid. Let's see, we obviously have, this is the z direction, so gravity acts downwards. 1, 2, 3, 4, 5. The diameter. I'm trying to save the space in the middle here, but we'll just use a different color. Okay, so its diameter here is d. So in one way, this is also, we can treat this as a really quick Chapter 7 review problem as well. So just from dimensional analysis, so this would be the thing. If you want to then do a experiment and can we determine what the viscosity of a fluid is? Dimensional analysis, therefore, our viscosity is some function of everything else. Density of the fluid, density of the sphere, the terminal velocity, the diameter, and gravity. 1, 2, 3, 4, 5, 6. R equals 3. If you run through this first, you see we have a diameter, which is a length. We have velocity, which is just length and time. And then we have densities, which is going to add that third thing. So we know we have 3 reference dimensions. Therefore, we'll have 3 pi terms. And by inspection, well, before we get to by inspection, let's choose 3 repeating variables, d, u, and we can't choose g, right? Because that's only length and time. These two together only make up length and time. Let's just choose density. By inspection, the first one, viscosity with d, u, and density. What can you make from viscosity with these 3? What? Oh. So picking them, I guess I just did it out loud here. But again, a key thing, start simple. So if there's something in your list, so you can't choose this, because that's going to be the dependent parameter. So then you have 5 to choose from, and you have to choose 3. Start simple. The diameter is just a length. That's as simple as you can get. Once you've taken that out, go as simple as you can beyond that. Is there another one that is just time, or is just force, or is just mass? Or if you have one that's just length and then just time. It's not all 3 of them altogether. Density involves, actually density if you're doing mass, it's just, okay, we'll just write it out. D is just in length. Velocity, I chose it because it's just length and time. And then density, I chose it because it's just mass and length. And so they're as simple as you can get. And actually, that's actually the only choice you can make here. You could choose the sphere density, but we can't choose G for that third one. It has to be one of these 2. I don't know. There's looking back at the last exam would be a better case where I told you what to choose. Maybe running through that and seeing if the simplicity idea works for that. I mean, you'll see it will. But by inspection here, when we have our list here for the first pi term is going to be in terms of a viscosity, a length scale, a velocity, and a density. If you go to your list of common ones, right, I think, heck, what I hope we leave here with is what a Reynolds number is and how it should just jump out at you if you see these four variables. Right, there's a few things that you should leave here with. An appreciation for Reynolds number, and generally what it means to flow inside and outside of objects, and how it relates viscous to the inertial forces. And then applications of ideas like Bernoulli's with losses in them, right? I mean, that's the last few bit, that's like what we've been dealing with a lot. All right, pi 2 is then if we go in, we now have the sphere density related to, can we do this one by inspection? It needs to include this one, right? So these are our non-repeating variables. Can you make a dimensionless parameter by multiplying or dividing this by one of these? Huh? So if they're the same quantities just for different things, you can just divide them, just like our aspect ratios, length over length, density over density. And pi 3, now we're going to g in terms of du and density. This is just length over time squared, and here we have our length and time ones. Well, you can see this will look just like the Froude number, or u squared over gd. Actually, this is Froude squared, but it's not meant to be the point of this problem, I guess. But you should be comfortable with doing this, and if you're not, it's fine to run through the the setting up your system of equations. But this is a time saver if you are comfortable with doing this. Okay, so instead, I want to make this a chapter 9 problem for external flow. So let's go back to our diagram, and we'll just treat this as our free body diagram. So you guys tell me, what are all the forces on this falling through the liquid? Weight, drag. So weight is going to act through the center here. We have drag there. Anything else? Is that it? They just equal each other? I'll tell you, we're not done. So if anyone's hesitating to respond. Buoyancy. Chapter 2 here. That's what's nice. See chapter 7, chapter 2, chapter 9, all coming together here. So that's it. So the red here is all of our forces. They all act along the center line, right, through symmetry, but had to move them out of the way. But they'll just be perfectly balancing each other. So sum of the forces in the z direction is 0, means that our drag plus our buoyant force must balance the weight. Buoyant force, so let's take each of them separately, and we'll start with the easiest ones. Let's go start with the weight. The weight is just the density of the sphere times gravity, so its specific weight times the volume over which that acts. And we'll just say over here, the volume of a sphere is just 4/3 pi r cubed, or d over 2 cubed. What is a buoyant force then? Weight of the fluid displaced, right? Same equation, we're just switching out the densities. Perfect. And our drag. How do we get drag here? Oh gosh, we have to be careful. Let me go back. Let me go all the way back and be artistic. Whoo! I don't want to confuse this with the diameter, so I'm going to put tails on my D. Make sense? Oh, God. I'm in. This is my 3rd hour of review session right now. So I hope that's all you guys are laughing at. All right. So you guys tell me, what is a drag force? Say it again. Weight minus a buoyant force. But how can we write it in terms of the other known quantities or the other quantities we want to relate this to? There it is. And times the area. So what is the area here? Pi r squared, but it's pi d squared over 4. Right? So it's the circle that the fluid sees. The projection of that sphere onto 2 dimensions is just a circle. I just thought, look on, yeah. I mean, I appreciate that. It seems like they said something right. Okay. So what's missing here? Let's see. We have an equation that relates these 3 guys. When we write them out, these are all quantities that were in our list of proper variables to use, except the only thing that wasn't there was this guy. So we needed to determine that. And we said this is a viscous fluid, and what we mean by that is that Reynolds number is very, very small. Reynolds number is less than 1. So we go to the proper table for really viscous flow, and again, this would be given to you. But we have on page 518, table 9.4, flow over certain things at low Reynolds number dependent coefficients. And we can see here, if it's really low Reynolds number, we can actually get the drag coefficient in terms of the Reynolds number itself. And so for flow over a sphere of diameter d, it's just 24 over the Reynolds number, where the Reynolds number is defined in terms of the diameter of the sphere. Beautiful. Rho ud over viscosity. And then this, that's the Reynolds number that we've had before. But okay, so therefore our drag is just 24 over 12. Let's just start plugging everything in here. So we have drag, which is 24 over rho u d viscosity. We have a half. We have rho u squared, and our area is pi d squared over 4. If we look, 4 and a 2 make 8 on the bottom. That's going to be 3 on the top. Viscosity is on the top. Density cancels. Our u, one of them cancels. So we're just left with 1 u. Our d, we're going to have only 1 d left on top and a pi. Three pi. All right, so let's just now plug everything in. We have our drag, which is 3 pi d u mu plus rho of our fluid, g, times 4/3. But that 4 is going to be swamped by 2 of these. We'll just have a 6 on the bottom, I hope. 2. Is that right? 6? You guys agree? 6 pi d cubed equals rho g over 6 pi, rho sphere d cubed. And what are we looking for? We're looking to solve for what the viscosity is, and that's right there. We get that by itself. We're just going to have, well, over on this right-hand side, these two terms are exactly the same except just different densities. So we just have g pi d cubed over 6 rho s minus density, and then just divide the whole thing by 3 pi du. Or viscosity equals 18. Our pi's cancel. Well, I'm going to be left with d squared and a g and a u on the bottom. So let's see, if I do this right, it'll be g d squared over 18u rho s minus rho. So that allows you to then just determine in terms of if you can weigh your fluid, in a container. Obviously, you can weigh a sphere just by putting it on a scale. You can measure the diameter of it, and then in the lab, measure its velocity as it falls and determine the viscosity of the fluid that it falls through. Yeah? 4/3 over 1/8, or 4/3 times 1/8. All right, kind of bookended it here. What do you guys want to go do now? Bookended the course, hydrostatics and drag. Potential flow? Right in the middle, actually. Oh, just about. Okay. All right, so this one I think I yanked off of the review document. So if you're an expert at that, is that all right? You chose it. So you are an expert at all the review problems? If that's the case, then these are not. Okay, good. That's what I figured. That comes off as being rude. Okay. So what this is that if we have these potential flows are funny. I mean, what's a source in real life? But if you have a source near some wall, so you can imagine. I think what they had is in one of your homework problems, it was a pond that looked like a half body, and then there was maybe a sink of fluid. Maybe the intake for a fountain that would later shoot it up off somewhere else. But what this needs to be is a two-dimensional flow, though. So it needs to be into the page a constant source with a bunch of holes in it, and there's just flow coming out of this pipe in all directions. But regardless, this is what we're trying to compare or to analyze here. And what the problem has is that two different locations that are separated by, let's call it little b. And in the statement, it gives numbers, but we'll see if we can avoid it. But the question is, what is the difference in pressure between A and B? If it makes sense to plug in numbers, we'll give them later. So you might think, and I don't know, I definitely wouldn't imagine, I wouldn't be expecting you to do this initial setup. In fact, it's given in the problem statement how to do this originally. But how do you take a source? We know what the potential flow solutions are for a source, but we don't have one for a wall. What we do here is, this is truly a wall, and that's what we're trying to represent physically. But instead, we put in a mirror image on this side. And what you can imagine is once the flow comes this way in any direction, this will then end up being a streamline. And flow can't cross a streamline, so this ends up being a perfect wall. And this is called the method of mirror imaging, the method of images. And then we can superpose these. And so it's really just this and this. Okay, so if we remember for a source, our velocity potential is a bit easier to use here, is just m over 2 pi times the natural log of the radius, where this is valid in the, where the radius comes out of the point source. Well, we're kind of, that would be easy for one of these, but not so easy for the other one. So it's going to be convenient to choose an origin point here and shift these both off of that origin symmetrically. And so we can then take advantage of that symmetry to do some things with. But it's also convenient at this point to say that this is also, let's see, how do we do this? If we take natural log of r, to shift this, we're going to need to shift it in the y direction. Right, so this is y, this is x. We need to shift our potential flow solution in the positive y direction and the negative y direction, and then add them together. That's going to be a little hard. Remember, r is the square root of x squared plus y squared. Well, let me write it more generally. R is the square root of x minus x naught plus y minus y naught if you're looking to shift it, right? Well, we're only going to be shifting in y. But this is hard. That square root makes it really difficult. So it's easier to get rid of the square root and write this in terms of r squared, and then shifts in x, in x. And then after the shift, you square the x and the y components. So natural log of r, I'm just going to claim here, this is the same as if you take natural log of r squared and divide it by 2. Right? Remember that exponents in a natural log, we just pull the 2 down. Make sense? Okay. So this is what we'll use for our source. And let's just say everything so far wouldn't be expected, but everything following would be. So for our point source our real source for our pipe, that's just going to be x minus a. I'm sorry, x squared plus y minus a squared. And for our image source here, this is r squared, is going to be x squared plus y plus a squared. Now, superposition. means that we can just add them together to get our full velocity potential. So this is m over 4 pi. They're equal, equal strength sources here. And then we have natural log of x squared plus y minus a squared plus natural log x squared plus y plus a squared. Remember, we're trying to get the pressure. To get the pressure, we need to apply Bernoulli's. Do we need to make sure that B and A are on the same streamline to apply Bernoulli's? No, actually, this is a potential flow, so we actually don't even need that. But they will be because this is a wall. So that represents there should be no flow across our wall. But regardless, to get to the application of Bernoulli's, to get pressure, to get some information about the dynamics of the flow, the pressure, we need to get all the velocities. And so that's why we went through and found the velocity potential, and then from there we can determine our velocities just through the definition. d phi dx. Okay, so this is going to be m over 4 pi times, here we have 1 over x squared plus y minus a squared, and then on top we just have 2x through the chain rule, plus, again, 2x over x squared plus y plus a squared. Okay, should we find v? V, which equals d phi dy. Well, here's maybe something with potential flow. Oftentimes you can just kind of skip over a step. We are only going to be finding the velocities at A and B. That's a wall. If we've done this correct, and we're telling you that if you put these two things here, you had better get no flow across it. So V should be 0 here. And actually, it wouldn't be too difficult to just do it, but you can see what's just going to happen is in the let's just do it. So then if we evaluate this, so that's V. If we evaluate V at y equals 0, what do we get? I just want to, this isn't jumping out at me. So let's see, maybe it is to you. Minus 2a over x squared plus a squared, there we go, plus 2a over x squared plus a squared. And that just equals 0. Okay, good. Whew. But you could, save some time by knowing that this represents a wall, and therefore there should be no flow across it. All right, so therefore our total speed, v, at the wall, for A or B, but we'll leave it as a function of x along the wall. So is just going to be our u as a function of x along the wall, but evaluated it at y equals 0, which is just going to be m over 4 pi 2x over x squared plus a squared plus 2x over x squared plus a squared, or we see that we'll just have the 4's cancel, which is just going to be mx over pi x squared plus a squared. All right, so that's the velocity at the wall as a function of x. So what is our velocity at b? Our total speed, I should say. That's just the velocity at the wall, as a function of x evaluated at x equals 0. If we just go back, x equals 0, and then a is just going to be evaluated at x equals b. We can see that when we plug in x equals 0, we just get 0. So that's a stagnation point. B is a stagnation point, which shouldn't be a surprise. Our velocity at A is then just the wall velocity as a function of x. You might as well just throw it in there, function of x. Evaluated at x equals b. And so we just have mb over pi b squared plus a squared. And the last step is then we can just Bernoulli's b to a. Those are at the same elevation, whether we're considering gravity or not. Typically, we don't in potential flow, but for elevation changes. But even if this was the direction of gravity, they're equal to each other, so we can definitely say that. And we already found that that's just 0. So therefore, our PB minus PA is just going to be gamma VA squared over 2G. Well, gamma is just rho G, so this is just going to be rho VA squared over 2. And I don't know, let's just leave it at that. We can plug in density m squared b squared 2 pi squared b squared plus a squared squared. How does that work? Satisfying answer.